Hello and welcome back. In this video, we'll take the concepts that we've learned in the past few videos and we'll apply them now to some problems from the textbook. So the first one we'll look at is OpenStax problem 616. And then we'll look at a more complicated problem, OpenStax problem 629. So 616 reads, Olympic ice skaters are able to spin at about 5 revolutions per second. That's giving us the angular speed or angular velocity. So we're given omega is equal to 5 revolutions per second. Revolution per second is not our standard unit, but it's another unit we can use. We could also have degrees per second or rotations per second. So that is the unit given to us in the problem statement. A asks, what is the angular velocity in radians per second? So in part A, we want to take this angular velocity and we'll want to convert the units to be radians per second instead of revolutions per second. Part B, what is the centripetal acceleration of the skater's nose if it is about 0.12 meters from the axis of rotation? So the axis of rotation is a line that goes through the center of his head down between his feet. And so to the tip of his nose, this distance from the axis of rotation to the tip of his nose, they're saying is 0.12 meters. So that's given. Remember, the symbol r is our distance from the axis of rotation symbol. So r is equal to 0.120 meters. C, an exceptional skater named Dick Button was able to spin much faster in the 1950s than anyone, about 9 revolutions per second. So this is a different angular velocity. This is for Dick Button. I'm putting a prime on it to distinguish it between this angular velocity. They're not the same, obviously. So he was able to spin at 9 revolutions per second. And it goes on to say, what is the centripetal acceleration of the tip of his nose if it's the same distance, 0.120 meters, from the axes of rotation? So that's going to be part C. And now D, comment on the magnitudes of the accelerations found. All right. And it went on further to say that Button, it is reputed that Button ruptured small blood vessels in his face during his spins. All right, so A, omega is 5 revolutions per second. All right, so we want to convert that 5 revolutions per second to radians per second. So I can only multiply by a ratio whose value is 1. So I want to get rid of revolutions. I put it in the denominator. And how many radians is the same as 1 revolution? 2 pi radians are the same as 1 revolution. So this ratio has a value of 1. So it's legal to multiply this number by this ratio and not change the meaning. The revolutions will cancel, and this is going to be 5 times 2, or 10 pi, and the units are radians per second. So here it is right here, and multiplying pi by 10, this is 31.4 radians per second. So that's part A, converting omega to standard units of radians per second. In part B now, we want to know what is the centripetal acceleration experienced by the tip of the nose if the tip of the nose is 0.120 meters from the axes of rotation. So remember that the centripetal acceleration can be written in terms of angular quantities as r omega squared. We already got omega in the units it must be in when we combine it with other quantities. Remember, when we're combining a quantity with other quantities, we need it in standard units. So we've already got our omega in standard units, so now we can just plug in. So here's r, here's omega, and I need to square all of omega, all the units and the number. Okay? So when I do that, I end up with 118 when I multiply 0.12 by 31.4 squared. And now what do we get for units? We get meters, radians squared per second squared. But remember, radians is that unit that can morph in and morph out. So the radians squared just goes away, and we express this as meters per second squared. That's the standard unit for acceleration. So that's the centripetal acceleration experienced by a person rotating at 5 revolutions per second. Now, Dick Button was rotating at 9 revolutions per second. And we want to find now what was the centripetal acceleration experienced by his tip of the nose. Well, we need to figure out, first of all, what is his angular velocity in standard units. So we're going to take our 9 revolutions per second, and we're going to multiply by that same ratio, 1 revolution in the denominator to get rid of the revolution in the numerator. And 1 revolution is the same as 2 pi radians. And so 9 times 2 gives us 18 times pi radians per second. Multiplying 18 by pi, we get about 56.52 radians per second for Dick Button's angular velocity in standard units. Now calculating his centripetal acceleration of the nose, 0.12 meters r times his omega squared, 56.52 radians per second, that whole thing squared. When you work out the numbers here, you'll come up with 383 meters per second squared. In part D now, we want to know what, talk a little bit about the magnitudes of these accelerations. And so it's very common when you're trying to look at how large an acceleration is to put it in units of g's. So remember, 1 g is the same as 9.80 meters per second squared. Okay, so when I take Dick Button's acceleration of 383 meters per second squared and I multiply it by a ratio whose value is 1, that would be 1g over 9.80 meters per second squared, using this equality to form that ratio, I come up with 39 g's. So the tip of his nose was experiencing an acceleration of 39 g's. It's quite large. And then I, for comparison, calculated the centripetal acceleration experienced by the tip of the nose of the person rotating at 5 revolutions per second. So again, took the centripetal acceleration, 118, multiplied by the ratio 1g is the same as 9.80 meters per second squared, come up with 12 g's. So this person also large acceleration experienced at the tip of the nose, but you know, less than a third of what Dick Button was. So very large still. All right, so the next problem is a little bit more comprehensive, and it has to do with a centrifuge. So there's a picture shown in the textbook, and I'll just read 29 and then we'll work on solving it. A large centrifuge, like the one shown in the figure, is used to expose aspiring astronauts to accelerations similar to those experienced in rocket launches and atmospheric reentries. A, what is the angular velocity? At what angular velocity is the centripetal acceleration 10 g's? So we are given that the centripetal acceleration is equal to 10 g's, and we want to find in part A what is the angular velocity. So for part A, omega equals question mark. And we're also given how far away the rider is from the axis of rotation, and we're told that he's 15 meters away from the axis of rotation. So that's given in the problem statement. And then in B, it says the rider's cage hangs on a pivot at the end of an arm allowed to swing out during the rotation. If you look in your textbook, you'll see the picture. So let's say here's the axis of rotation. Here's the arm that's allowed to swing out, and now here's the rider. So that is the rider. Okay, this is the axis of rotation. All right. And so we want to know the rider's cage hangs on a pivot arm at the end of the arm allowed to swing out during the rotation is shown. At what angle below the horizontal will the cage hang if the centripetal acceleration is 10 g's? So this angle right here below the horizontal is what we want to find, theta. So we want to find what is that angle theta. All right, so here's the rider. And let's look at what forces are being exerted on the rider. So if we just take the rider, so we want an FBD for rider. And remember, in part B, we want to find what theta is from our drawing. So here's our free body diagram for the rider. Okay, the seat is swung out, okay? The seat can still only push at a perpendicular orientation to its surface. So that means that there's going to be a normal force being exerted by the seat that is perpendicular to the seat itself. So the seat looks like that. So there is the normal force being exerted. And then what other forces are being exerted on the rider? Well, then other than the seat, the only other thing in contact with him is the Earth's gravitational field. So that's the force of gravity. So remember, we can write the force of gravity as mg, the rider's mass times the acceleration due to Earth's gravity. So this is our free body diagram. These are the forces acting on the rider. We want to find this angle theta. Okay, and that angle theta, you can see, is sitting right there. That's the angle theta. So first of all, we need to choose a coordinate system, because you can see that these forces are not lying along a line. So recall that in the previous video we talked about, when we have circular motion, choosing the axes to be tangential and centripetal. So in this